Welcome to qnawire.
This is problem 74 of chapter 23. This problem asks us to find the resolution limit for a hawk, and all we're given is the height of the hawk. So let's call this capital H hawk. We're given this as 50 centimeters. And from the reading, we know that the diameter of a human eye, let's go ahead and write this as d human, is 5.0 millimeters. So for this problem, if you can find the diameter for a hawk's pupil, go ahead and use that. Otherwise, what I'm going to do here is calculate the diameter of a hawk's pupil based on a proportional argument. So if we scale a human down to the size of a hawk, we're going to use a proportional argument to determine the pupil of a hawk. Again, this is going to be an estimation. So the average height of a human is approximately 175 centimeters. So let's set up a proportion. Let's say the diameter of a human pupil in relation to the height of a human is going to be equal to the diameter of a hawk's pupil in proportion to their height. So here we're going to go ahead and solve for d hawk, and this is going to be the pupil size of the hawk. We multiply both sides by h hawk to get d hawk is equal to d human h hawk over h human. So the assumption we're making here is that a human is scaled down to a hawk size. The proportions are going to be kept the same. That may or may not be true, but this is done for estimation purposes. Let's go ahead and plug in all the values. Here for d human we have 5 millimeters. We have 50 centimeters for the height of the hawk. And we have 175 centimeters for the height of a human. So a rough estimation for the hawk's pupil size comes out to 1.4 millimeters. So this is what we're going to use to determine the resolution limit of a hawk. The equation that we need is theta res is equal to 1.22 lambda over d. We are going to use this d hawk for d. Now we need to select a lambda. So the visible spectrum for birds, they can see some light waves that we can't. So even the average light wave, the average wavelength for visible light comes out to 560 nanometers. We can round that down to 500 for birds, for hawks, if we take into account that they can see into the ultraviolet range, which we can't. So let's pick 500 nanometers for the wavelength of a hawk. Again, you could pick something along that order as long as it's near visible light. On the order we should be fine. Here I'm picking 500 nanometers, which is equal to 500 times 10 to the negative 9 meters. Let's go ahead and plug everything in here. We have 1.22 times lambda, so this is the light coming in, over d, which is 1.4 millimeters. Now millimeters is 1.4 times 10 to the negative 3 meters. That way we could have meters cancel out with meters, and then we're going to have an angle here in radians. When we evaluate that, we got approximately 4.27 times 10 to the negative 4 radians. Now of all the answer choices, B comes closest to it with 3 times 10 to the -4 radians. So if we chose a different lambda, we could get a value closer to this. However, there was no way knowing ahead of time what to pick there for lambda. Also, compare this 3 times 10 to the -4 radians with the answer that we got, and you can see that the other ones are different orders from our answer here. So the resolution limit for a hawk, if the hawk is 50 centimeters tall, we did a proportional argument to find the pupil size of the hawk to be this quantity here, 1.4 millimeters, and then we plug that into this theta res formula using 500 nanometers for our wavelength. This concludes problem 74.